Hello dears, today I am going to discuss the topic energy of an harmonic oscillator. We know that a oscillator or a body having finite mass is moving, so definitely it have a moving energy. The energy due to its motion is called kinetic energy. Due to the position of the oscillator, it possesses an energy called potential energy. Here, the potential energy is evolved due to the finite compression or elongation of the spring. So, we can say that a harmonic oscillator possesses two types of energies. One is kinetic energy and the other is potential energy. Potential energy is due to its displacement from the mean position and kinetic energy is due to its velocity. At any instant, the total energy of the oscillator is the sum of kinetic energy and the potential energy. So, now we are going to derive the equations for kinetic energy and the potential energy. First of all, let's look at the equation for potential energy. Consider a spring mass system. This is moving. So, every time spring is experiencing compression and elongation. So, of course, there is a force. When the oscillator is displaced through dx distance, it will experience a work because we are pulling up the string. So, some amount of work has to be done. Then the total work done, that will be dW. That is dW equal to force applied into displacement. That is dW is equal to F dx. We know that for a spring, the restoring force F developed inside the spring is directly proportional to the displacement x. That is F directly proportional to x. That is F equal to kx. So now we can replace the F in this equation as kx. That is dW equal to kx into dx. Then now imagine that the body is moved from the point O to some distance x. Then we can find the total work done on the spring to displace by a distance x. So the work done we can find by taking the integral of dW. That is integral 0 to x dW equal to integral 0 to x kx dx. Here kx is a constant. So taking outside, so we get W equal to k into integral 0 to x dx. Here integral x dx is simply x square by 2. So putting this and applying the limit 0 and x, we get W equal to half k x square. In short, we got the total work done displaced the spring from mean position to the x distance. It shows that work done depends upon the displacement and it vary with the time because x will vary with the time. So obviously work done also vary with the time. Or this work done is stored as the potential energy in the spring. Now we are going to find the expression for kinetic energy. We know that when the spring is oscillating, it is moving with some different velocity. Of course, the velocity will changes with the time. So still we can find the kinetic energy. Here we have the kinetic energy expression, that is half mv square. Here we have already derived the velocity part, that is v equal to omega 0 root of a square minus x square. So substituting the v in equation number 1, we get kinetic energy equal to half m into omega 0 root of a square minus x square all raised to 2. That is, squaring the velocity term, we get kinetic energy equal to half m omega 0 square into a square minus x square. Here we got the expression for kinetic energy. Kinetic energy depends on the position, and it shows that kinetic energy also varies with the position of the oscillator. So now we have the expression for kinetic energy and the potential energy. Then we can find the expression for total energy also. We know that total energy is the sum of potential energy and the kinetic energy. We have already derived the equation for kinetic energy and the potential energy. Kinetic energy equal to half m omega 0 square into a square minus x square, and the potential energy equal to half k x square. So, total energy is equal to half k x square plus half m omega 0 square into a square minus x square. Then half kx square plus half m omega 0 square a square minus half m omega 0 square x square. We have already studied that omega 0 square is equal to k by m. So, k is equal to omega 0 square into m. So, substituting k equal to omega 0 square m in this equation, we got E total equal to half k square plus half k a square minus half k x square. So, half k square and minus half k square will be cancelled. Therefore, total equal to half k a square. We have k equal to m omega 0 square. So, substituting k equal to m omega 0 square in half k square, that is E total equal to half m omega 0 square a square. So, here we got the expression for total energy. Here we can see that mass is a constant, omega 0 square is a constant, and also amplitude is also a constant. It implies that the total energy of an harmonic oscillator is a constant. Even though the potential energy and the kinetic energy, they vary with respect to time, but when you add up both, the total energy of the oscillator became a constant. And from the equation we can see that the total energy is directly proportional to the square of the amplitude of the oscillator, that is E total directly proportional to a square. So now we can plot the energies. Take two axes, a horizontal axis with the position and vertical axis with the energy. So firstly take potential energy is equal to half kx square. If you take x along the horizontal axis and potential energy along the vertical axis, we can see that half kx square will be a parabolic curve. This is the potential energy curve, and this curve is symmetric with respect to energy axis. At the mean position, parabolic curve is 0. It means that potential energy will be 0 at the mean position, and at the maximum x will be equal to a. Then going to the kinetic energy part, we can see the inverted daughter curves. In this equation, when we put x is equal to 0, we can see that kinetic energy is maximum at the mean position, and when we put x is equal to a, the kinetic energy is minimum. That is, harmonic oscillator stops at the extreme point. They don't possess any kinetic energy at the extreme point. And we can set that from graph, Both kinetic energy and potential energy are equal at the middle point. In short, we can say that potential energy is maximum at x is equal to A and minimum at x is equal to 0. Kinetic energy is maximum at x is equal to 0 and minimum at x is equal to A. So, let me recall the topics. We have discussed the energy of harmonic oscillator, then the expression for potential energy and the kinetic energy, then we discussed the expression for total energy, and finally we plot a curve for potential energy and the kinetic energy. So, thank you for watching.